Let's start today by taking a look at this article. And my question is, what is the main claim in this article? Well, it's in the headline. 53% of Americans support raising the federal minimum wage to $15. They're saying 53% of all Americans. And my question is, how did they get this 53%? Did they ask all Americans? I know they didn't ask me, so who did they ask to get this 53%? And if we skim all the way to the end here, it does say here that the poll sampled 802 American adults. So they asked only 802 people, which is a really small number compared to all Americans, which is going to be millions and millions of people. So how are they able to say 53% of all Americans from just asking 802 people? So that's one of the questions we're going to answer today. Another question we're going to answer is, in this next sentence, it says the margin of error is plus or minus 3.5 percentage points. What does that mean? The researchers here are admitting that because they didn't ask all Americans and they only asked 802 people, they're saying that they could be off by plus or minus 3.5%. So they're saying that it may not be exactly 53%. They could be off by plus or minus 3.5%. So they're saying that it could be as low as 53 minus 3.5, which is 49.5%. And it could be as high as 53 plus 3.5, which is 56.5%. So the researchers are saying that it may not be exactly 53%, but they are saying that it's somewhere between 49.5% and 56.5%. But still, how did they get this 3.5%? Did they just make that up? And then finally, what is this 95% confidence level? So this is an example of what's called a confidence interval, which is going to be the focus for our next unit. How do we construct a confidence interval? So here's the procedure for constructing a CI. CI here just stands for confidence interval for a population proportion. So today we're interested in the proportion of the population that has a certain characteristic. So in the article, they were interested in the proportion of Americans that supported raising the minimum wage. Step 1, compute the point estimate p-hat. So as is often the case in statistics, you can't get data from everybody in the population. There's just too many people. So in the article, they didn't ask all Americans, right? That would be millions and millions of people, too many. So instead, they took a sample of 802 people and then got their percent or proportion from the sample. That's the p-hat. So in the article, that 53% that they got is the p-hat. Next step, find a critical value z star based on the confidence level. So for this step, we're going to be drawing the normal distribution picture. And the confidence level refers to the area in the middle. So we're going to be shading our picture in the middle for all the questions today. So the confidence level refers to the area that's in the middle. So in the article, the confidence level they were using was 95%. Okay, that refers to the area in the middle. So as a decimal, 95% is 0.95. That's the area in the middle. And the critical value, z star just means the special z that has an area of 0.95 in the middle. That's the critical value. And then step 3 is to compute the margin of error. So this is the plus minus 3.5% in the article. And this is how they found it. Z star, which you got from step 2, big square root, p-hat, which you got from step 1, 1 minus p-hat over n. N here is the sample size. How many people did you ask? And then finally, step 4, construct the confidence interval by doing p-hat plus or minus the margin of error. So now, let me skip to example 1 on the third page. Example 1. A newspaper polls 238 voters and 137 of them said they would support the funding of the new CRC library building. Part A, construct a 95% confidence interval for the proportion of voters who support the funding of the new CRC library building. The first step in constructing a confidence interval will be to compute the point estimate p hat. Okay, so first step will be finding p hat. And p hat is the proportion that we get from our sample. So we asked 238 voters total, and 137 of them said they would support the new CRC library building. So the proportion from our sample will be 137 out of the total number of people that we asked, 238. Okay, on a calculator, 137 over 238. Okay, round to 3 decimal places, this will be 0.576. And as a percent, that's going to be 57.6%. So from our sample, 57.6% of the voters support the new CRC library building. Step 2. Step 2 would be to find a critical value Z star based on the confidence level. So we'll be drawing a normal distribution picture and shading in the middle. The confidence level refers to the area shaded in the middle. So our confidence level here is 95% confidence. So as a decimal, that would be 0.95. That's the area in the middle. And what we're looking for is we're looking for the 2 Z stars that would have an area of 0.95 in the middle. So really, this part is just an area to Z type question. And in our last unit, we talked about area to X type questions. And as part of that process, we did area to Z by doing a Q-norm left area. So that's what we need here. Q-norm left area. What is the left area? It's not 0.95 because 0.95 is the shaded part in the middle. What I want is this unshaded part on the left side. So how do you find the unshaded part on the left side? If I know 0.95 is the shaded area in the middle, I can do 1 minus. And that should give me the unshaded part, which is the left and right together. So start off by doing 1 minus 0.95. That's 0.05. Okay, that's the unshaded part, which is the left and right together. Because I only want the left one, divided by 2. Okay, 0.05 divided by 2. 0.025. Okay, that's the unshaded part on the left side, which is what I'm going to plug into Q-norm. So in R, we're going to do Q-norm 0.025. This should get me a Z star. Round to 3 decimal places here. This is negative 1. This is going to go up to 960. So from my picture, I expect 2 Z stars. Negative 1.960 would be the one on the left. The one on the right, just by symmetry of the picture, is going to be positive. So positive 1.960. So those are my 2 Z stars, my 2 critical values. The next step would be to find a margin of error using this formula for E. Okay. So step 3, we're going to find the margin of error. Okay, formula says Z star. I have 2 Z stars here. I always use the positive one, so use the positive one. So positive 1.960, big square root. Inside the square root, p hat, which is our answer from step 1. P hat will be 0.576. 1 minus p hat, so 1 minus 0.576. Over n. N is our sample size, so how many people did we ask total? 238. Okay, so make sure when you write this out that the entire fraction is inside the square root. Okay, now on our calculator. So 1.960 square root. And I recommend clicking on the fraction button right after square root so that you have the fraction inside the square root. Up top, 0.576, parentheses, 1 minus, 0.576, close parentheses on the bottom, 238. Okay, make sure that the entire fraction is inside the square root and that the square root bar goes across the entire thing. And I get 0.063. So round to 3 decimal places here also. Okay, step 4. Step 4 is to construct the confidence interval by doing p hat plus or minus the margin of error, e. P hat is from step 1, 0.576, plus or minus the margin of error, e, from step 3, 0.063. And then to get my final interval, I'm going to subtract and add. So to get my low number, 0.576 minus 0.063. Okay, that gets me my low number, 0.513. And to get my upper number, add 0.576 plus 0.063, 0.639. Okay, and that's my final answer that I want. Okay, so what we're saying here is that even though we only asked 238 people and we didn't ask every single voter, we're saying here that if we were able to ask every single voter, the true proportion is going to be somewhere between 0.513 and 0.639. Part B, interpret your result in part A in a complete sentence. So this is the sentence I want you to write for all of these. So start off by saying we are, state your confidence level. So in this problem, we are 95% confidence. So we are 95% confident that, and for this question, we're talking about the proportion of voters who support funding the new CRC library building. So I'm just going to copy that part. The proportion of voters who support the funding of the new CRC library building. We are 95% confident that the proportion of voters who support the funding of the new CRC library building. Okay, we are 95% confident that the proportion of voters who support the funding of the new CRC library building is between. And then you're going to state your confidence interval. But when you write the sentence, I want you to convert it to a percent. Okay, so 0.513 as a percent would be 51.3%. And 0.639 as a percent would be 63.9%. So what we're saying here is that even though we didn't ask every single voter, and we only asked 238 voters, if we were able to ask every single voter, the true percent will be somewhere between 51.3% and 63.9%. So now let's try to answer some of the questions on the next page. Part C. Based on the confidence interval, can you conclude that more than 50% of the voters support the funding of the new CRC library building? Going back to the sentence that we just wrote, we don't know what the true percent is, but our confidence interval is telling us that the true percent is somewhere between 51.3% and 63.9%. So knowing just that, can we say that the true percent is going to be more than 50%? And really the question we're asking here is, are all the numbers in our confidence interval more than 50? Yes. 51.3 is definitely more than 50. 63.9 is more than 50. So all the numbers in between are definitely going to be more than 50 also. So we can say for sure that yes, the true percent is going to be more than 50%. And if you're a newspaper, you can now predict the election, right? So because you know that the true percent is going to be more than 50%, you can say that the CRC library building is going to win the election. And that was from asking just 238 voters, right? We didn't ask every single voter. We only asked 238 voters. And from that, we're able to predict the outcome of the election. Confidence intervals allow us to make a prediction about the entire population, which is everybody, from just data that we got from a smaller sample. So that's pretty cool. Part D. Based on a confidence interval, can you conclude that more than 55% of the voters support the funding of the new CRC library building? So going back to our confidence interval, are all the numbers in our confidence interval more than 55? No. 51.3% is definitely not more than 55. So because not every number in our confidence interval is more than 55, this would be a no. Part E. Based on a confidence interval, can you conclude that less than 60% of the voters support the new CRC library building? So looking at our confidence interval, are all of the numbers in our confidence interval less than 60%? No, right? 63.9% is definitely not less than 60. So not every number in our confidence interval is less than 60. It's going to be a no. Part F, based on a confidence interval, can you conclude that less than 65% of the voters support the new CRC library building? So ask yourself, are all the numbers in our confidence interval less than 65? Yes. 51.3, definitely less than 65%. 63.9, definitely less than 65. So all the numbers in between are definitely going to be less than 65 also. This is going to be yes. Okay, so before we move on to parts G and H, let me take a pause here and talk about what does it mean for us to be 95% confident. Interpretation of the confidence level. Let me use 95% confidence as the example. So what does this 95% confidence mean? So in the example that we just did, we went through the process of finding a confidence interval. So if we repeat this process many times, and what I mean here is take a sample and then make a confidence interval. And to be more concrete about this, let's go back to example one. So in example one, we went through the process and got a confidence interval. If I repeat this process again, in other words, I'll take another sample of 238 voters. So in the new sample, there will probably be a different number of people that support the new CRC library building, which means I'll get a different p-hat, I'll get a different margin of error, and I'll get a different confidence interval at the end. If I repeat this process many times, I'll get a whole bunch of different confidence intervals. 95% confidence is saying that 95% of those intervals will catch the true population proportion. In other words, we will catch the true population proportion (95% of the time). Which is what this picture here is trying to illustrate. The vertical line represents the true population proportion. And notice that most of these intervals catches the true population proportion in the middle. So 95% of the time, the confidence intervals will catch the true population proportion, which means that 5% of the time, you are going to get an interval that misses, which is what this one represents here. It doesn't have the true population proportion in the middle. This part's not in your handouts, so don't worry about writing this down. So we know how to find a confidence interval by going through those 4 steps. What I want to do here is talk a little bit about why that process works. We're trying to catch the true population proportion, P. And this proportion comes from a population that we know nothing about. So the distribution for this population could look very wild. But we don't really care. We don't really care because we have this central limit theorem that we talked about in the last unit. And the central limit theorem says that as long as we pick a sample size big enough, the distribution is going to look like this. And it's going to have a mean that matches the mean of the original population. So instead of trying to catch this P, I'm going to try to catch this P because they're the same. Now, where does this 95% confidence come in? The 95% confidence level is referring to the area in the middle. And in the last unit, we talked about area to x type questions, where I gave you an area of 0.95, and you found the 2 x's that had an area of 0.95 in the middle. Okay? For confidence intervals, I don't really care about those x's. What I really care about is the distance from the middle to the edge. So what's the distance from the middle to the edge? So let's talk about how we found those x's in the last unit. So to find those x's, what we did was we did an area to x question, and at the very end, we used this x formula, which says x equals mu, which is the mean or the middle, plus z times the standard deviation. So this z times the standard deviation is telling you how far to go up from the middle to get to the edge. So the distance from the middle to the edge is really just the z times standard deviation part. Okay? And what is this z times standard deviation part for the proportion situation? Z times the standard deviation is z times this square root formula. Okay? Z times this square root formula should look kind of familiar because z times that big square root formula is exactly the formula that we use for the margin of error. Z times the big square root formula. So the margin of error is really the distance from the middle to the edge. That's the margin of error. Now, what do I know about this picture? I know that if I take a sample and look at the proportion, I get this p hat. This p hat is probably not exactly equal to p. That would be hard, right? That would be like hitting a bullseye. What I do know is that 95% of the time, if I take a sample and look at the proportion, I'm going to land inside this shaded area. Okay, say I land right here. So I didn't hit the true proportion exactly like I wanted, but if I go up and down using the margin of error, so p hat plus the margin of error, p hat minus the margin of error. So that's exactly what we did in the very last step to make our final interval, right? We subtracted and added the margin of error. So if we do that, we end up with an interval that does catch the true population proportion. So 95% of the time, if we take a sample, look at p hat, we're going to land inside the shaded area. And if we land inside the shaded area and we go up and down using the margin of error, we get an interval that does catch the true population proportion 95% of the time. And that's why the process works. There's 2 things that affect the width of the interval and the margin of error. The first thing is the sample size. So if you use a larger sample size, what happens? So let's take a look at the formula for margin of error again. So if we use a larger sample size is n. So if we are using a larger sample size, you will be dividing by a larger number. So when you divide by a larger number, overall, you'll get a smaller number. So overall, you'll get a smaller margin of error. So using a larger sample size results in a smaller margin of error. And because the margin of error is used to do plus and minus to construct our final interval, smaller error is going to result in a narrower interval. And then if you use a smaller sample size, you'll get the reverse effect. So you'll get a larger error. And a larger error means a wider interval. The second thing that affects the width and the margin of error is going to be the confidence level. So if you use a larger confidence level, what happens? So going back to the front page here, confidence level, remember, refers to the area in the middle. So if you're using a larger confidence level, the area in the middle is larger, which means your z-stars will be bigger. So z-star is being multiplied. So if you're multiplying by a bigger number, overall, you'll get a bigger number for the margin of error. So a larger confidence level will result in a larger margin of error. And a larger margin of error means you have a wider interval. If you use a smaller confidence level, you'll have the reverse effect. So you'll have a smaller error. Which means you'll have a narrower interval. So the moral of the story is the confidence level is a measure of how likely we are to catch the true population proportion. So we want a high level of confidence. And in the real world, you'll see mostly 95% confidence, 99% confidence, sometimes 90% confidence. But what we just talked about on this page here is that the higher the confidence level, the larger the error. We don't want a large error. So what do? Well, sample size. So what we talked about here is that a higher sample size, smaller error. So the way you compensate for a high level of confidence is pick a larger sample size because that will reduce the error. Okay, so this is the information we need to solve parts G and H on example 1. Okay, picking up where we left off on example 1, part G. If the sample size were 300 rather than 238, would the width of the interval be wider or narrower than the result in part A? So originally, we used a sample size of 238. If the new sample size were 300, what happens? So if we're using a 300 instead of 238, that represents a larger sample size. What happens with a larger sample size? So looking at the notes that we just took, a larger sample size results in a smaller error and a narrower interval. So narrower interval. But remember, the reasoning behind that was, so originally we were using 238 as our sample size, which is right here. If we replace that with a 300, right, we would be dividing by a larger number. Dividing by a larger number results in a smaller number overall, which is why the margin of error will be smaller. And a smaller margin of error would result in a narrower interval. Part H. If the confidence level were 98% rather than 95%, would the margin of error be larger or smaller than the result in part A? So originally, we were using 95%. If the new confidence level were 98%, what happens? So if the new one's 98%, then we are using a larger confidence level. So a larger confidence level results in a larger error and a wider interval. So a larger error. But remember, what's the reasoning behind that? So the reasoning, the confidence level has to do with the area in the middle, right? So in the original, we were using an area of 0.95. If the new confidence level were 98%, then this new area would be 0.98. So a bigger area. Bigger area would mean the z-stars will be bigger. Okay, z-star is multiplying. So if you multiply by a bigger number, overall, you'll get a bigger number for the margin of error. So that's why it's larger. Example 2. A survey is to be conducted in which a random sample of residents in Sacramento will be asked whether they favor or oppose making the 2 years of community college free. How many residents should be polled to be sure that a 90% confidence interval for the proportion who favor free community college will have a margin of error of 0.05. Now this example differs from example 1 that we just did. In example 1, we were asked to find a confidence interval. This example is asking for how many residents should be polled. In other words, it's asking for a sample size. So this represents something you would do in the planning stages of a study. So you're trying to plan out how many people you should include in your sample so that when you do a 90% confidence interval, you'll get a margin of error of 0.05. So for this example, we'll need a formula for the sample size. To get a formula for the sample size, I'm going to start off with our formula for the margin of error. So let me recopy this formula. So the margin of error is z star, big square root, p hat, 1 minus p hat over n. N here is the sample size. So what I'm going to do is do some algebra and get the n by itself. So don't worry about following these algebra steps. The formula you need is going to be at the end in a box. So to get the n by itself, the first thing I'm going to do is I'm going to divide both sides by z star. Okay, so I'll get e over z star. On the right side, when I divide by z star, the z star is going to go away, and I'll just have the big square root. Okay, next thing, if I want to get the n by itself, is to get rid of this square root. To get rid of a square root, we're going to square both sides. So squaring both sides, left side is going to be e over z star squared. On the right side, when I square it, the square root is going to go away. So I'll have p hat, 1 minus p hat over n. Next thing I'm going to do is I'm going to multiply the n over to the other side. So I'll get n e over z star squared equals p hat 1 minus p hat. Okay, I'm almost done. I want the n by itself, so I need to get rid of this e over z star squared. So I'm going to divide both sides by e over z star squared. Okay, so the left side would now be n, right side p hat 1 minus p hat. Okay, dividing by e over z star squared, or divided by a fraction, is the same thing as multiplying by the reciprocal. So multiplying by the reciprocal, so reciprocal just means flipped. So multiplying by the reciprocal would be z star over e squared. So n is by itself, and that's our formula for the sample size. So in this formula, z star, so z star has to do with the confidence level, e is the margin of error, p hat, what's p hat? P hat is the proportion you get from the sample. But remember, we're looking for a sample size because we're in the planning stages of the study. So we don't have a sample yet. So if we don't have a sample yet, what do you use for p hat? Well, if a prior estimate for p hat exists, so if someone else have done the study already and they have an estimate for p hat, we're going to use it. So what do you do when there's not a prior estimate for p hat? Okay, so if there's no prior estimate for p hat, then we're going to use the next best thing, which is a p-hat of 50%, or a p-hat of, as a decimal, 0.50. So why 0.50? Well, for students who know a little bit of calculus, if you try to maximize this function, you'll see that you get a maximum when p-hat is 0.50. So in other words, 0.50 is the p-hat that will result in the largest sample size. So if you don't know anything about p-hat, you're going to do the safest thing, which is to use the largest sample size, which happens when p-hat is 0.50. Now that we have a formula for the sample size, we can do example 2. Part A. A previous survey suggests that the proportion who favor free community college is 84%. Using this estimate, what sample size is needed? So we're looking for a sample size, which means we're going to be using the formula for sample size. So let me recopy the formula for the sample size. So n equals p-hat, 1 minus p-hat, z star over e squared. And what do we plug in for these letters? Let me start with the z star. Z star has to do with the confidence level and this picture. Okay, we're always shading in the middle. The area in the middle is the confidence level. So what confidence level are we using here? 90% confidence. So our confidence level is 90%. 90% as a decimal is 0.90. And we're looking for the two z stars that have an area of 0.90 in the middle. This is really a area to z type question. For an area to z, we do Q norm. And we feed it the left area. What's the left area here? It's not 0.90, because 0.90 is the area in the middle. So I want this unshaded part on the left here. So if 0.90 is the shaded area in the middle, if I do 1 minus, that should give me the unshaded part. So let's start off by doing 1 minus. So 1 minus 0.90 is 0.1. Okay, that's the unshaded part, which is the left and right together. I just want the left part divided by 2. So 0.1 divided by 2. 0.05. That's the area of the left unshaded part, which is what I need to plug into Q norm. So we're going to do Q norm 0.05. Okay, in R, Q norm 0.05. Okay, this should give me a z star. Okay, so z star here is round to 3 decimal places. This is negative 1.645. And from my picture, I expect 2 z stars. The negative 1.645 is the one on the left. The one on the right should be the positive version of that. So positive 1.645. Okay, that's z star. E is the margin of error. What margin of error am I using here? Margin of error 0.05. Okay, so that goes in for the E. And then finally, what do we use for p-hat? So let's go back to the formula for sample size. What to use for p-hat? If a prior estimate for p-hat exists, use it. If no prior estimate for p-hat exists, we're going to use p-hat 0.50. So part A says a previous survey suggests that the proportion who favor free community college is 84%. So we are given here a prior estimate for p-hat. So since we have a prior estimate, we're going to use it. So we're going to use 84% for the p-hat. P-hat as a decimal, 84% is 0.84. 1 minus p-hat is going to be 1 minus 0.84. Z star, I have 2 z stars, but I always use the positive one. So we're going to use the positive 1.645. Over E, margin of error, we said margin of error was 0.05. And then don't forget the square. Okay, so on a calculator, 0.84, 1 minus 0.84, 1.645 over 0.05, close parentheses, don't forget the square, and I get 145.476. We're not done because I'm looking for a sample size. So in other words, I'm looking for how many people to include in my sample. It doesn't make sense to have decimals. It doesn't make sense to have 0.476 people. So the question is, how do we round? So we're not going to round the usual way. And here's why. So 145.476 is the sample size that will get us exactly a margin of error of 0.05. Okay? If I round the usual way, this would round to 145. So 145 will represent a smaller sample size. But a smaller sample size, we said, gives us a larger error. We don't want that. Okay? We want a smaller error. So smaller error, we need to use a larger sample size. So we need to go larger here, always. So we're always going to round up. So this is going to round up to 146. Okay, so if you end up with decimals here, don't round the usual way. You're always going to round up. Part B. Estimate the sample size needed if no estimate of P is available. Okay, so same situation. This time, we don't have an estimate for the proportion. If no prior estimate for p hat exists, use a p hat of 0.50. So same setup. The only thing that's different is instead of 0.84 for the p hat, we're going to be using 0.50 for the p hat. So everything else is going to be the same. So instead of 0.84, we're going to do 0.50, 1 minus 0.50. The z star is going to stay the same, so 1.645 over the margin of error is the same, 0.05, and don't forget the square. So on a calculator, 0.50, 1 minus 0.50, 1.645 over 0.05, close parentheses, don't forget the square, 270.603. Okay, we're talking about how many people we should ask for a sample. Does it make sense to have decimals? Does it make sense to have 0.603? How do we round? Always round up. So we're going to round up to 271. Okay, so when we're planning this study, if we're going to use a 90% confidence interval and we want a margin of error of 0.05, we would need to ask 271 people. If we don't know anything about P, if we do know something about P, we would need 146 people. Part C. If the survey wanted to estimate the proportion of the entire state of California rather than just Sacramento, who favor free community college, would the necessary sample size be larger, smaller, or the same? So in this question, we were talking about the proportion of people in Sacramento. Okay, and we found that we needed 146 people and 271 people. Now, if we wanted to know the proportion in the entire state of California, would we need more, less, or the same number of people? What do you think? Well, if I change this Sacramento to California, what changes? We still want a 90% confidence interval. We still want a margin of error of 0.05. Okay, so that takes care of the z star and the e. Okay, those should be the same. In part A, we're still using 84% as our prior estimate. In part B, with no estimate, we're still going to use 0.50. So what changes? If I change this to California, nothing in our calculation changes. So you get exactly the same answer. If I change Sacramento to the entire world, still nothing changes, and you still get the same answer. Okay, so still the same answer. Which is counterintuitive, because you would think that because the population of California is so much bigger than just Sacramento, you would need more people. But the reality is you don't. Which brings me to the rho of population size. So population size has no effect on the sample size needed. So whether we're talking about just Sacramento, California, the entire US, or even the entire world, you would still only need 271 people in the worst case scenario, which is pretty cool. Example 3. Joe and Sally are going to construct confidence intervals from the same simple random sample. Joe's confidence interval will have level 90% and Sally's will have level 95%. Part A. Which confidence interval will have the larger margin of error? Or would they both be the same? So Joe and Sally are using the same simple random sample, so they're using the same sample size. The only difference is that Joe is going to use a 90% confidence level, and Sally is going to use a 95% confidence level. So the question is, which confidence level will result in a larger margin of error? So we're talking about confidence levels, and the way I think about it is I know confidence levels have to do with this picture. And the area in the middle is the confidence level. So which area in the middle, 90% or 95%, will result in a larger margin of error? So larger margin of error is the same thing as saying a wider interval. So which one is going to give you a wider margin of error, wider interval? So for this to be wider, the area will be bigger. So you want the bigger area. Which one is the bigger area? The 95%. This will be the 95%, which is Sally's. If you need to, go back to the notes. We're talking about which confidence level will get you a larger error. So larger error will be the larger confidence level. The larger confidence level will be the 95%. Part B. Which confidence interval is more likely to contain the population proportion? Or are they both equally likely to do so? So in other words, which confidence level, 90% or 95%, is more likely to catch the true population proportion? So let's go back to when we talked about the interpretation of the confidence level. We said that 95% confidence means that we will catch the true population proportion 95% of the time. So the confidence level is how likely you are to catch the true population proportion. So the larger confidence level will be more likely to catch the true population proportion. So we want the larger confidence level, which will be 95%. Which is also Sally's. Have a great day. See you next time.